Okay, so last time we finished with the definition and examples of generators and cogenerators. So today we're going to prove several statements that use this notion of generator and cogenerator. So first proposition, so let C be a co-complete category. So recall that the co-complete means that we have all small co-limits. So suppose we have a set of objects. So then the following conditions are equivalent. So first condition is that this set of objects is a generating set. So second, well, since the category is co-complete, we can introduce new object G, which is just the co-product of all the objects that we have in this set. Since this is a set, this is a small co-limit, so it exists in this category. And this co-product is a generator. In the category C. So this means that for co-complete categories, there is no really much difference between the generating set and just a generator. If you have a generating set, you can always take a co-product and get the generator. And of course, the generator is just a generating set with only one object. So probably the most interesting condition is condition 3, which says that for any object X in the category C, there is a set, I'm going to call this set S, and epimorphism in this category from the G to the S to the object X. Do I need to remind you what this notation means? It means that I just take a coproduct of as many copies of G as it has elements in the set S. Okay. So for the proof, I want to say that the fact that condition 1 and 2 are equivalent is quite easy to understand. So 1 is equivalent to 2. Well, there was a characterization of a generator in terms of the main representable functor being faithful. So here we can just notice that the product of such representable functors for each I is the same as the functor representable by the coproduct of the objects Gi. Right? And hence, if the functors are the same, left-hand side is faithful if and only if the right-hand side is faithful. And that's essentially the end of the proof that 1 is equivalent to 2. Now let's show that 2 is equivalent to 3. And we're going to separate this in 2 steps. First we show that 2 implies 3, and then the other way around. So we need to show that for any object X, there is a set and there is such epimorphism. Well, the set is easy to define. So I just say that by definition, set S that I'm going to use here is just the set of all maps in the category C from the generator G to the given object X. Now, the map that I need to define, so map P. Well, since this is a coproduct, right? So for a coproduct, if I want to define a map from a coproduct to any other object, it is enough to say what are the compositions with the canonical injections. right? So here I have a canonical, say I have some copy of G. There is a canonical injection that I'm going to call I sub F. So here the set S parameterizing this coproduct is just a set of maps. So this, on one hand, I can think about this F as an index, and I'm using this F as an index in this notation. But on the other hand, I know also that this F is just a map from the G to the X. So this is map F. And that's enough to define map P, right? Because now I'm just saying that by definition, P composition with the canonical injection IF is F. And since I know all such compositions for any index F, I know the map P by the universal property. Okay, so that's the definition of P. Now let's check that this is an epimorphism. So suppose we have the following fork diagram. So we have G to the S, map to the X, and then there are two other maps. I'm going to call these maps G, so G and G prime. So two other maps to some object Y, and if we assume that, well, composition of the G and P is the same as the composition of the G prime and P, but G is not equal to the G prime, right? So I'm assuming that this is not an epimorphism. So I want to get some contradiction from this. Well, I can claim that there is map H in the category C from the generator G to the X, such that if I take composition of the G with H and the G prime with H, I'll get two different maps. Do you see why there is such an H? Yeah, this is exactly the definition of a generator, right? For a generator, we're supposed to have a map from the generator to the X such that the compositions for two different maps, in this case G and G prime, these precompositions with H are different. So that's just the definition of a generator. So, but on the other hand, so let me say, but the composition of the G and H, well, I can understand this as the composition of the G and the projection, the decomposition with the IH. Right, so the way we define this will be precisely as the same thing as the product of the G and H. And the same for the second one. Right, so the G prime H, I can also rewrite as the G prime P IH. Yeah, but now I know that these two maps are the same, right? And I just take precomposition with the same map, which is just IH. Hence, I can conclude that the GH is the same as the G prime H, which is a contradiction. Okay, so this proves that this map is an epimorphism. And this finishes the proof that 2 implies 3. Now let's go in the other direction and show that 3 implies 2. Okay, so now I know that there is such an epimorphism P. So suppose I have two maps. Again, I'm going to call them G and G prime. So G is not equal to the G prime, and this lives in the home set in the category C. So maps from the X to the Y. Well, since we know that this is an epimorphism, so P is an epimorphism, we can conclude that the composition of the G with P and G prime with P are two different maps. But so GH, so if these are two different maps, well, I can say the following. I can say that there is at least one index, so there is little s in the set large S, such that GPIS is not equal to the G prime PIS. If the maps are different, there is at least one component where these maps are different, right? But that's exactly what we need to show if you want to conclude that object 2, well, object in the condition 2 is a generator. That's exactly the condition. So this finishes the proof that these three conditions are equivalent. And sometimes people take this third condition in this proposition as a definition. I think there are many texts where this is taken as a definition, and it's also quite natural, right? For example, if you compare this, well, if you look at the example of the R modules, it is very natural, for example, that the ring R is a generator, because any other module can be presented, well, as a quotient of some free module by some submodule. So that's exactly what we have in the condition 3. Okay, to formulate and prove next theorem, I need to introduce a couple of the notions. So definition, a category, is called well-powered if isomorphism classes of sub-objects of any object, well, let's call this category C, of any object in C, form a set. So of course, all natural examples of categories that you know, like for example sets, groups, monoids, rings, modules, they all well-powered. And another terminology that I'm going to use is the following. The definition, which is really just a terminology, a category is called balanced if a map образует множество. Но это означает, что класс, который мы рассматриваем, это множество. Ну, здесь речь идет все-таки про объекты в категории, да? Мы знаем, что во всех разумных примерах категорий, таких рабочих, с которыми пользуемся, все-таки объекты же не образуют множество. Ну, да, в категории множества объекты не образуют множество. Здесь у нас мы выбираем под объекты какого-то одного объекта. А априори, если вы берете какую-то непонятную категорию, совершенно не следует, что они образуют множество. Это то, что мы определяли раньше. Это просто вы берете объект и мономорфизм в данный объект. Такая пара — это подобъект. Да. Okay, so a category is called balanced if a map in this category is an isomorphism if and only if it is an epimorphism and also monomorphism. Again, we know that for this definition, there are plenty of examples of the categories that are not balanced. We discussed such examples in the beginning of this course. Okay, so now we have the notion of well-powered, we have balanced. Well, to formulate the next theorem, I also need the notion of the intersections. So we can say that it's not really a definition, just to remind you that suppose we have two sub-objects. Well, let's maybe call them B and B prime. So there is object B, monomorphism into some object C, and there is another B prime and a monomorphism to the same object C. So we can introduce the intersection of two sub-objects. So these are sub-objects. That since these two maps are mono, this is by definition sub-objects of the object C. So the intersection of the, well, in this case, two sub-objects, but you can immediately generalize this to any set of sub-objects. Well, you just take the corresponding pullback. You have two embeddings, take the pullback, and the pullback you by definition call the intersection of two sub-objects. We saw that this makes sense in the category of sets, and if it's not a category of sets, just any category, you just take this as a definition of the intersection. Well, and notice that my declaration on all the errors are correct. I assume that this is mono and this is mono, and we proved a general theorem that being this arrow being a mono implies that this is a mono, and the same for this, of course, by symmetry. So this is indeed a sub-object, so this intersection is sub-object in the B prime and the sub-object in the B, so hence automatically as a composition of mono is mono, is sub-object in C. Я думаю, это правда, да, но лучше нужно это проверить на всякий случай. Okay. So next theorem. Let's see, be a balanced category with finite intersections and a set of generators so then C is well powered. Аналогии с чем? Ну, называйте множество сепараторов, какая разница? Но они генерируют категорию в том смысле, что они различают все стрелки. Если вы хотите аналогию, там как какая-то группа генерируется или кольцо, я не думаю, что это возможно. Okay, so let's prove this. Oh, by the way, in this statement there is finite intersection, but really this is the same thing as the binary intersections that we have in this kind of definition, it's the same condition. So let's assume that we have this, that we have two sub-objects that I'm going, as before, call B and B prime. So C is an object in this category, and I consider two subobjects. B is subobject in C, B prime is subobject in C. And of course I want to assume that these two subobjects are not isomorphic. So then I also want to give a name for this map. So let me call this map I, and the second map will be I prime. So then I can form the intersection, I can form the corresponding pullback. So I'll have B embedded into C, there is B prime embedded into C, there is the intersection of the B. So this is map I, this is I prime, and I also want to call these maps J prime and G. So these are the four monomorphisms in the pullback diagram. So first of all, I can notice quite elementary thing. If J and J prime are both epimorphisms, then I get a contradiction, right? Since I know that the category is balanced, I know that these two maps are monomorphisms. If they both are also epimorphisms, it just means that this is isomorphism and this is isomorphism. Hence, these two objects are isomorphic. So then, since C is balanced, I can conclude that the B prime is isomorphic to the intersection, and this intersection also is isomorphic to B, which is a contradiction. So without loss of generality, I can assume that at least one of these J's is not an epimorphism. So I'm going to suppose that J is not an epimorphism. Well, if this is not an epimorphism, let's just use the definition and write what it means. Right? So it means that we can find two maps. So there is F and there is G, which are two different maps, such that we can take the intersection. It is embedded with the map J into the object B, and then there are maps to different maps F and G to some other object that I'm going to call D, and such that the compositions are the same. So F composition with J is the same as the G composition with J. Okay, so these two maps are different. So then I claim that I can find, well, first of all, I can find an index, little I, in the set I, and then for this index, I can find the map H from the GI to the object B, such that the composition of the FH is different from the composition of the G and H. Right? So why I can find such index and H? Yeah, by the same reason as before when I asked such a question, because this is a generating set. So if I have two maps, two different maps, I can always find such the map H. So I can also draw this on the diagram. So there is this H somewhere, H from the GI. So the question is it possible to take this map H and factor this map H through the map J? Can I find such a factorization? No, what happens if I can find such factorization? Oh, if there is such factorization, right, I can, instead of going like this, taking composition with F and G, I can just go like this, taking precomposition with the J. And I know that taking such precomposition is the same. So that would be a contradiction with this condition. So that's not possible. So H can be factored through the intersection of the B and B prime. Okay? So if there is no such factorization, I can conclude that there is no map H prime from the GI to the B prime such that I prime H prime is not equal to the IH. No, indeed, if I assume that there is such map H prime, right, it means that I can go back to this pullback diagram, draw GI here, so there is map H, so there is map H prime. So, а почему нет? Ну, нет, ну, в смысле, идея доказательства в том, что я просто нашел такой индекс, и я с этим индексом работаю до конца доказательства. Я знаю, что он есть, хотя бы один, и мне этого достаточно. Сейчас, здесь, кстати, равно. Well, I'm just saying that I can find such H, right? I know that I can't factor this H through the intersection. Now I claim that from the non-existence of such factorization, I can claim that there is I can claim that there is no such H prime with the property that they have this equality, right? Because if I have such H prime, since this is a pullback, I can find this factorization that can't exist. So this is kind of some preliminary work, and now we're going to see how this allows us to complete the proof. So I'm just defining the map phi of the object B to be, by definition, the following set. So this is the set of all maps in the category C from the GI, the same GI that we found before, to the given object B. We can think about this as the map from the class of sub-objects of the given object C, so the sub-object is B, to the sub. So we can consider this as a subset inside set of all maps between GI and the object C. Right, so we can consider this as a subset because the map from the B to the C is a monomorphism. So this is just this map here is just taking composition with the I, with the embedding of the sub-object B into the object C. So if you want to think about this, we can say that phi is a map from the class of the sub-objects of the C to the CGI-C, to the set of all subsets of this given set of all maps. Yes, that's the assumption. No, all categories in this course are locally locally small, meaning that all the home sets are just sets. Okay. So now what we proved by that argument is that if I take this map phi, compute this on some object B, I take another object which is, well, actually, to be precise, it's not sub-objects of C, this is kind of isomorphism classes, of course. Isomorphism classes of sub-objects of C. So I can compute this map phi on one sub-object, or I can compute this map phi on the other sub-object B prime, and I can see that the answers are different. And why the answers are different? Well, that's precisely that argument. We precisely constructed an element H which is in this set, but it's not in this set. Hence, these two sets are different. So we take a class and we can interpret this class as the subset in this set. Hence, this is not a class, this is a set. So isomorphism classes of subobjects form a set. Okay. And sometimes this is called the theorem about electrification. So this joke makes sense in English. So you have a category with a generator, so it is well powered. Okay, and we need this theorem to discuss adjoint functor theorems. So adjoint So there are several versions of the adjoint functor theorems. Before we formulate even the first one, we need the following lemma, which is kind of a completely trivial lemma if you just look at what we have in the statement. So suppose we have two, so let A and B be two complete categories. And we also have two continuous functors. Well, I didn't introduce the notion of continuous functor, so let me maybe write this as a definition before the statement. So definition, a functor is called continuous if it preserves all small limits. You can clearly see the analogy with the continuous functions. Continuous functor. Yeah. Like a function. Function is continuous if it preserves limits. Or at least if the topology is sufficiently nice. Okay, so a little technical lemma, which I think is complete triviality. So let A and B be complete categories. Suppose I have two continuous functors. F is a continuous functor from A to the category C, and G is a continuous functor from the category B to the category C. So these are continuous functors. Well, then the comma category for these two functors F and G is also complete. And from the comma category, you have two projection functors or forgetful functors. So on forgetful functors from the comma category to the A and from the comma category to the B, are also continuous. Well, when I say continuous functors, it means that I'm assuming that I consider only small limits. But if I drop this assumption from this condition and I just say that these two functors preserves all limits, of course the conclusion will be, and for example, if I say that in the categories A and B, I also have all limits, then again the conclusion will be that in the comma category, I also have all limits, and the projection functors are preserving all limits. So this is kind of just a version of the same lemma. And the proof is very easy. Well, if you remember the definition of a comma category, the objects are like diagrams of this form. You have functor, you apply this to some object A, it lives in the category A. You have a second functor G, you apply this to some other object that lives in the category B, and there is a map between these two objects. So this is a map in the category C. But now, suppose, well, that's just how an object in this comma category looks like, just to remind you. Now suppose I have a diagram, so such objects. So this is all parameterized by some indexing category. And I want to take the limit of this indexing category of such diagram. Well, I think it requires some formal proof, definitely, but the proof is so silly that I'm going to skip this and just write clearly, and that the answer is just you take the limit here, right? So you take the, well, or maybe even since the f is continuous, you can just write this as a limit of AI, and then you apply f. So here there will be some limiting map f, and here there will be g that is applied to the limit of the objects bi. It's not a formal proof, but this is what you get if you do the formal computation, which I'm leaving to you. Ну, потому что все, что здесь есть, все непрерывное, все функторы непрерывные. Здесь совершенно тавтологичное упражнение. Ну, напишите, что у вас будет лимитирующий конус здесь, и вы просто увидите, что это то же самое, что здесь. Okay. So first adjoint functor theorem. Well, sometimes this is called the primeval adjoint functor theorem. Yes, for the shortness for the adjoint functor theorems, I'm going to just write A of t. So in this theorem, we suppose that D has all limits. And when I say all limits, that means that not necessarily small, just all possible limits over classes, not necessarily even sets. So a functor G from the category D to some other category C has left adjoint if and only if G preserves all limits. Okay, so for the proof in one direction, of course, there is nothing really to show. So in one direction, if you assume that there is the corresponding left adjoint, so this functor G is the right adjoint, and any right adjoint preserve all limits. Now in the other direction, well, we can take the comma category for some object C and the functor G. So here C is just an object in the category C. And so in this category, well, this category has all limits, right? That is by the previous lemma. This is just a special case of a comma category. So there are all limits in this comma category, right? But this implies that this comma category has an initial object. That's probably the only non-trivial step in this proof. Right, so the reason why this category has an initial object, well, because the initial object I can present as a limit. Right, so this is clearly a co-limit, right, for the empty diagram, but also this is a limit. So the problem with this limit, that this is not a small limit. So initial object can be presented as the limit of the identity functor on some category. So since, well, in this case, well, let me maybe write something different, maybe something like T. In this case, T that I want to take is this comma category, right? And this, you can notice that the problem with this limit that this is not a small limit, but for this category I assume that you have all limits, so this is not really a problem. But the fact that the initial object is the limit of the identity functor, I want to leave this for the seminar. I think this is a nice, one of the nice exercises. And here I'm just using this exercise, and in fact I already finished the proof, right? Because now I only need to use another theorem that we proved at the end of the first chapter when we characterized the adjoint functors as the initial objects in such categories. So if there are initial objects in this category, there is an adjoint functor. So that's the end of the proof. So it looks like a nice theorem, right? There you have this criterion for the existence of an adjoint functor. So with this theorem, there is only one problem. So remark / exercise that this assumption that you have all limits is too strong. So a category that has all limits is thin, which means that in this category, if you look at the Hom set between any two objects, then there are at most one arrow between any two objects. So this is for any x and y in the objects of C. So really, this is not a theorem that is useful in any practical applications. But this gives you the main idea of what you want to call adjoint functor theorems and how you want to kind of formulate those theorems. What you want to take is that you want to suppose that instead of having all limits, you have only small limits, right? And this functor, instead of preserving all limits, preserve only small limits, right? So you modify these two conditions. Of course, the theorem won't be correct in this form, and then you need to add some another assumptions. When you add some another assumptions, you get various versions of the adjoint functor theorems. So we're going to discuss today the so-called special adjoint functor theorem. And for this, we're going to need one more lemma. lemma. So if D is a complete well-powered category with a cogenerator Q, so then D as an initial object. Okay, so for the proof, I'm just start with an object. So I want to show, so the goal of the proof is to show that this object R, which is by definition just the intersection of all the sub-objects X of the cogenerator Q. So I want to show that this R is an initial object. So I can separate this proof into two steps. So on the first step, I'm going to show that if I consider, say, in this category D, home set between two objects, say R and D, then this set has at most one element. And then in this step 2, I will show that such set is always non-empty. Hence, this is an initial object. Okay, so for the first step, yeah, so this is for any D which is an object in the category D. Thank you. Okay, so suppose we have two maps. So let's take R, D, and two maps that I'm going to call F and G. Right? Then for these two maps, we can take the equalizer, so E with the map little e. So this pair is the equalizer of the two maps. Okay, so I want to show that actually F is the same as G, right? So I take any two maps and I want to show that if I have any two maps, they coincide. Well, the reason for this is that, so we know that in general, the map in any equalizer is a monomorphism, right? So this E is a sub-object in the R, and R is the intersection of all the sub-objects in the Q. So in fact, this is the smallest sub-object in the Q, and we constructed even sub-object in the smallest object. So hence, this monomorphism is in fact an isomorphism. And if this is an isomorphism, then F is the same as G. So this finishes the step 1, and we can go to the step 2. So in the step 2, I need to show that there is at least one map. So I take, as before, well, maybe a formulation of the step 2. So for any D, which is an object in the category D, there is a map from the R to D. So I can take this D. Well, I proved the theorem for the generators, but if I go to the opposite category, I have this similar statement for the cogenerators. So I can embed any object into the sum power of the cogenerator. So this is the first proposition that I proved on the today's lecture, but I apply this proposition to the opposite category. So instead of working with the generators, I work now with these co-generators, and instead of the epimorphism, I have monomorphism, and instead of the co-product, I now have just product. So everything is opposite. So I can embed this into some power of the Q. Now, and in fact, as I said, as before, I can take the set of all the maps from the object D to the co-generator Q. The proof will work with this set. Okay. So now I look at the pullback diagram. So I have D, which is a sub-object in the Q to the S. Now I take Q, and from the Q, I have the canonical diagonal map delta from the Q to the S, and then I can take the pullback. So the pullback gives me some object T, which is by construction a sub-object in the co-generator Q. Right, so then, since this is a sub-object, I know that R can be embedded into this sub-object. R is the smallest sub-object of Q, and T is just some sub-object of Q. So I can take this composition of the, T, yeah, and T is mapped not to the Q, to the D. Hence, I've constructed for any object D some map from the object R. Just taking composition, so T is mapped to the D, so this is just this map, and I take the composition which is R, which is sub-object of the T, and well, this is a non-trivial map from the R to the D. Okay. Questions about this proof? Well, I'm trying to show that whenever I take an object, I can construct a non-trivial map from the R to this object. So at the end, this composition will be the answer. This is non-trivial map. To get this, I do the following. I look at the first proposition I proved on today's lecture. I go to the opposite category, and this is the statement. I can embed any object as a sub-object into some power of the co-generator. Now here, this is this embedding. Now this map is just the map delta, the diagonal map for the product in this case. Well, it's just infinite product, but still delta exists. Now I take the pullback, so this is the pullback diagram. So there is some object T. Now this object T has a non-trivial map to the D, this map, and I just take a composition of this map T to the D, which the embedding of the R into the T. I can see that T is a sub-object in the Q, and R is the intersection of all the sub-objects. Clearly, I have a map from the R to the T. So this composition is a non-trivial map from the R to the D. Yeah, we're using it all the time. Well, here, for example, I need products. Here I have equalizers, and I have products and equalizers. I have all limits. Okay, so that's the lemma that we're going to need in the special adjoint functor theorem. So theorem. So this is special adjoint functor theorem. So let D be a complete well-powered category with a co-generator Q. So a functor F, yeah, I'm going to call this G. So a functor G from G to this C has left adjoint if and only if G is continuous. So you can see that this is a significant improvement if you compare this with the primeval AFT, right? So here the category is only complete, so there are only small limits. Well, additionally, we have to assume that this is well powered, which is not really such a strict assumption. I think most of the natural categories are well powered, but it has cogenerator, and we already know some examples of natural categories like groups and rings without cogenerators. So that in some applications this might be a restriction. And then the conclusion is very nice, that you can characterize the existence of a left adjoint in terms of the preserving the limits. Okay, so proof. Well, as before, in one direction this is automatic. This is just right adjoint preserve the limit. So of course the proof is in the other direction. Okay, so we'll look at the category of course, as before, we need to look at this comma category for the object C and functor G. So C is just some object in the category C. And for this category, we need to show several properties. For example, well, I need to show that for any C, this category has an initial object. Right? Then by the theorem from the end of the first chapter, I can conclude that there is a left adjoint. Well, if I want to use this lemma, I can say in this lemma three conditions: that this category has to be complete, well powered, and has a cogenerator. So that's essentially what we're going to check in this proof. So again, I can, if you wish, separate this into several steps. For example, step 1 will be that this category is complete. Which I want to say that this is clear, right? Since this is just a special case of the lemma that I formulate in the beginning of this section about adjoint functor theorems. So the fact that this is complete is a trivial observation. Now what we need is to show that, so step 2, you want to show that this comma category is well powered. And to do this, we will show a difference statement, which immediately implies this one. And the statement is that the forgetful functor from the comma category to the category D preserves monomorphisms and sometimes this is what is called reflects monomorphisms. So preserves monomorphisms means just if I have a monomorphism in this category, I apply the functor, I still get a monomorphism. And reflects means that if I have a map, I apply the functor, I get a monomorphism. It means that this map that I started with was actually a monomorphism. So reflects is kind of reading in the other direction. Okay, well, what we can say about the preserving of the monomorphisms? Well, we can notice that the projection of the forgetful functor preserves all limits, and if the functor preserves all limits, it preserves monomorphisms. Well, by just this observation that whenever we have monomorphism. So F is monomorphism if and only if this is a pullback square. So being a monomorphism is a property that can be characterized in terms of a limits, right? So the limits are preserved, and if you apply a functor, well, clearly the identity is also preserved by any functor. So it will be a diagram again of the same form, but for the F you just apply the forgetful functor. So hence this will be again a pullback, since pullback is a limit and limits are preserved. And it means that the image of a monomorphism is again a monomorphism. So this is what we need for the preservation of the limits. Now in the other direction is actually much easier. It's kind of a tautological statement. Well, suppose we have the following diagram. So that's just a diagram for the, if I want to check that something is a monomorphism in the comma category. So I have a map in this comma category, right? So, and suppose I have now F double prime that maps to the G D double prime and two maps G of K and the G of K prime. Right, so if I want to check that this is a monomorphism, I need to assume that G of the HK is the same as the G of the HK prime, right? And if I know that H is a mono, HK is equal to the HK prime, so hence K is equal to the K prime, right? And it means that, of course, the G of K is the same as the G of K prime. So if I know that H is a monomorphism, then I can also conclude that this diagram represents the monomorphism in the comma category. So the forgetful functor preserves monos and reflects monos, and hence if we know that the D is well powered, we can conclude that the comma category is also well powered, right? Because the being mono is the same thing. So this finishes the proof of the step 2. And finally, for the step 3, we need a family of cogenerators. Well, for the family of the cogenerators, I'm going to take V, and this will be the home set in the category C. So from all the objects, so the object C is fixed, and I take all the homes from the object C to the G of the cogenerator Q. So since I can interpret this, if I have an element in this home set, this is the same thing as the map from the C to the G of Q, right? So I can interpret an element in this home set as an object in the comma category. So this is object in the comma category. So in this sense, when I consider this set V, I actually consider this as a set of objects in the comma category. Okay, and now I take C. Let's take some diagrams. So we have C, F, G of some object D, so some object in the comma category. Now for this object D, I can find an embedding, so let's call this J to the Q to the S by the same reasoning as before. So this J is monomorphism. And now I just look at the following diagram. I have C, so this is F, G of D, and here I have G of the Q to the S, so this is G of JF, and this is G of J. Okay, so since J was a monomorphism, this is also a monomorphism. And what I can see that I can take any object, being this diagram, and I can embed this as some object into this object, right, which is this diagram. And this is of the form that I wanted it to be. So this V is a set of cogenerators. By the same reasoning, G, we know that G preserving limits, right? And hence it preserves pullbacks, and hence by the same reasoning it preserves monomorphisms. So this is a monomorphism. And that's the end of the proof. We checked all the three properties that we need in the lemma. So for any object C, there's an initial object, and hence there is an adjoint functor. Okay, so we have another 10 minutes. I want to look at the several examples of the special adjoint functor theorem. So examples. So first example, we take a forgetful functor U from the compact Hausdorff spaces to the O-topological spaces. So this C house is supposed to be compact Hausdorff topological spaces. Okay, now let's check that all the assumptions of the theorem, of the special adjoint functor theorem, are satisfied, and this functor has the corresponding, what's called left to right. So let me check. Yeah, it has left adjoint functor. Well, for example, how do you know that this category C house is complete? Why? Yeah, and how about the equalizers?
It follows from the fact that Pavlov is equivalent to the fact that the diagram map is cross-embedded, right?
Mm-hmm. And how this follows?
We need to check that a set on which the two maps are equal is a closed subset,
Mm-hmm.
and it's a preimage of the appropriate notebook, isn't it right?
I think probably something like this is right, but I think there is much simple explanation. If you just look at the diagram of the equalizer, what you'll see is that this equalizer E will be embedded as a closed subset into X, right? And X is a compact and Hausdorff, and a closed subset, and this again has to be compact and Hausdorff. So let me maybe write this. So the products in the compact and Hausdorff spaces exist by Tikhonov's theorem. So now if you look at the equalizer, so we take equalizer for any two maps. Well, first of all, this E, the way we define the equalizers in topological spaces, E is closed in the X, and hence E is compact, and also this is automatically Hausdorff. Hence there are equalizers, hence this is a complete category. So see, Hausdorff is complete. Well, clearly this is well powered, so I need to maybe underline this. So clearly is well powered. Okay, so what about the code generator?
So, when is it always right that E is closed? I guess it follows from the fact that it is closed.
Sorry, what's the question?
The fact that E is closed is always the case, right? Or does it matter that?
Well, it follows from the way we describe equalizers in the topological spaces. Yeah, so the only question that remains is to show that this category has a code generator. So what's a code generator in this category? Well, what if I take just the closed interval between 0 and 1? So this is a code generator, and how the statement you usually call that this interval is a code generator in this category. Well, usually this is called Urson's lemma. The statement that this interval is the code generator in the category, this is precisely, if you think about this, the Urson's lemma. So that's the Urson's lemma, and the conclusion is, since all the conditions of the theorem are satisfied, we can claim cogenerator. Hence, there is beta, which is left adjoint to the U. And what's the standard name for this beta? For the left adjoint functor for the forget. Yeah. So this is Stone-Chekhov quantification. And moreover, you can also notice that if you go back to this proof actually gives you a formula for the adjoint functor, if you carefully look at the steps that we do. And if you apply this formula for this Stone-Chekhov quantification, you exactly get the standard, one of the two standard definitions of the Stone-Chekhov quantification. But I think we're out of time, so let's take a break and continue this discussion next week.